Alright, welcome to our lecture over matter and energy. So matter is anything that has mass and takes up space. So if you touch the table is made out of matter. The coffee cup sitting on the table is made of matter, the coffee is made of matter, and you are made out of matter. Molecular theory just describes how matter makes up everyday objects that are all around us. Molecular theory says that matter is made up of these small invisible units called atoms. And this is not a chemistry class. We do have to cover some chemistry so you can understand what's going on, but please do not take this as college level chemistry 101. This is just a basic introduction to give you an understanding of how chemicals interact so that we can do our ecology side of the work. So we need to look at what atoms are and how atoms function. So atoms are small particles held together by energy. At the center of the atom is the nuclear region, the nucleus, and this is a densely packed region, and around it are the electrons, the electron cloud, and it looks like a diffuse blue area on this slide. Now, we need to know about electrons because the electrons have no mass and they move through space. These massless energy particles, or electrons, are what electricity is. Electricity is moving electrons. So if we know that electrons are found around the outside of atoms, and we can make those electrons move in a direction that we dictate, we can produce electricity. The center part of the atom, that's the nucleus. And that's made out of the protons and the neutrons. And from here you can see that the protons are positively charged and they have mass, and the neutrons have no charge, they're neutral, and they have mass. Now, what's key here is that in most atoms, the number of protons and the number of neutrons is exactly the same. There's no difference in them. They balance out. Now notice that the numbers of protons and the number of neutrons tell us what type of atom we have. And there are 92 common types of atom. Now, people have made more in nuclear reactions and stuff like that, but there's about 92 normal, common atoms. If a substance is made up of just one kind of atom, that substance is called an element. So gold is an element. The only thing in gold is gold atoms. Silver is an element. The only thing within the silver is silver atoms. Iron is an element. The only thing within the iron is iron atoms. But you know that if you leave iron out, it doesn't stay as iron. It becomes rusty. And that rust is not just iron atoms. It's iron mixed with oxygen atoms, mixed with hydrogen atoms. So if you have a collection of atoms, you don't have an element. There you have a molecule. Now, before I move on to molecules, I've got to quickly talk about isotopes. Now, I said on the last slide that in most atoms they have the same number of protons and the same number of neutrons. And if they have equal numbers of protons and neutrons, they tend to be very stable in their atomic structure. The atoms are very stable. Occasionally, we get atoms that have extra neutrons. They have more neutrons than normal. And these atoms with extra neutrons are called isotopes. Now, having extra neutrons makes them a little bit unstable. And the way that they can get back to stability is to get rid of those extra neutrons. And the neutrons can decay. They can break down. And Albert Einstein made the famous equation E equals mc squared. E, energy, equals m, matter, times c, which is a constant, and it's the speed of light, squared. So E equals mc squared. And that basically says that energy can be made from matter. So here we've got extra neutrons in our atom. And to become stable, they've got to get rid of them. How do they get rid of them? They can make them into energy. And this is what nuclear decay is. This is what we harness in a nuclear power plant. We harness the breakdown of neutrons. So if we understand atomic structure, we can understand which atoms to look for nuclear decay, make those atoms decay to give out large amounts of energy, and it comes out mostly as heat, and then use that heat to produce electricity, to cause electrons to flow in the way that we want them to flow so that we can have electricity. So atomic structure and isotopes is definitely important for our power generation within our society. Alright, back to molecules and matter. So we know that elements are made out of just one type of atom, and we know that molecules are made out of more than one type of atom, and those atoms are bonded together, they're joined together. So in the picture here we've got sodium chloride, normal table salt. You can see that it's atoms of sodium, Na+, actually sodium ions, but we don't need to go into that amount of detail. It's sodium bonded to atoms of chlorine. So we've got NAs joined to Cls and we get sodium chloride. Now, this is not a chemistry class, as I said. We don't have to go into all these different types of bonds and all the way that molecules form. All we need to know is that for most of the world, we don't find pure matter. In most of the world, we find matter as molecules. So wood is not made of an element, it's made out of molecules. Soil is a vast mixture of different chemicals. Plastics are mixtures of different chemicals. And it's the way that these mixtures come together that has real importance for this class. Matter has quality. There's high quality matter and there's low quality matter. High quality matter, that's matter with lots of the same atoms in a very confined space. So if we look at the second one down on the high quality side, it's salt. It's the sodium chloride from our last slide. And one thing we can think about is getting a set of molecular tweezers. And these are just made up. But if you can imagine having a set of tweezers that went down to such a fine point, you could reach into a chemical and pick out just one atom. So you could take some salt, reach into the salt and pick out one atom from that molecule. Well, your chance of picking a sodium atom out of salt is 50%. Half the atoms in there is sodium. So you could reach in and pretty much guarantee that you're going to collect some sodium. It's easy to get to. High quality matter. At the bottom we can see the soda can. Now I'm English, so I would say aluminium. You might say aluminum, but I'm afraid you'll have to put up with my English twang on this. So if we take the soda can and we use those same molecular tweezers, we reach into the metal of the can and grab an atom, it's going to be an aluminium atom. That's what's in there, and it's high quality because every time we pick one of the atoms out, it's going to be aluminium. It's easy to collect. Now if we scoot over onto the low quality side and think about the salt in water, then if we do that same trick with the molecular tweezers, when we've got seawater, salt and water mixed together, the chance of you grabbing that sodium ion is very small. You're very likely to grab one of the water molecules, an oxygen atom or a hydrogen atom, or one of the magnesium atoms, or one of the other atoms that are in there. So it's not as concentrated, it's not as easy to pick out your type of atom, so it's low quality. And if we go to the bottom, we have aluminium ore, and that's called a rock called bauxite. Well, that looks like a piece of rock. It's light brownish with red specks in it, rock. And there's not just aluminium. There's carbon, there's hydrogen, there's iron, there's titanium, there's aluminium, there's copper, there's sodium, there's chlorine, there's oxygen, there's tons of different atoms. So again, that's low quality matter. Now for our class, Here comes the kicker. Our modern society survives by taking low quality matter and turning it into high quality matter. We take aluminium ore and turn it into aluminium. We take iron ore and turn it into iron. We turn the iron into steel. We take copper ore and turn it into copper. We take oil and turn it into plastics. We take oil and turn it into gasoline. So we spend lots and lots of energy. We spend lots of our time converting low quality matter into high quality matter. All of the cans that are in your pantry are all high quality matter. The body of your car is high quality matter. If you're sitting at a table where it's a metal frame table like it would be if you were in the classroom, then that's high quality matter. All of the wires that run around your house are high quality matter. The pots and pans that you're using are high quality matter. What your refrigerator's made of is high quality matter. All of the wires and the particles of your TV, high quality matter, and we can just keep on going. Well, it takes a lot of energy to turn low quality matter into high quality matter. And modern society is very good at doing it. The problem becomes, what do you do with it when you've run out of useful work for the high quality matter you have? And the example we'll use is the soda can. We spend tons of energy creating our soda can, and when we're done drinking the soda, what should we do with that matter now? What should we do with the can now? And most people just throw it away, which means we have thrown away our high quality matter, so we have to go back out into the world, collect more iron ore, spend all that energy converting it into high quality aluminium again, and then make a new aluminium can. That is not sustainable. That does not meet the standard of environmental science, producing a sustainable environment. If we have high quality matter, you should never throw that away. That should never be lost from our energy stream, our matter stream. We should take our can, recycle it into a can. We should take our car, recycle it into usable metal. We should take our pots and pans and recycle them. We should take all of that high quality matter and recycle it. Now I know here in Milledgeville, lots and lots of people do that. They collect cans and they recycle them. They collect copper wire and they recycle them. Sometimes they don't even wait until the building's built or they own the copper wire. They just go and steal it and recycle it. So it does happen. But as a society as a whole, we do not recycle our high quality matter anywhere near the amount we should be to produce a sustainable society. So that's just one way of looking at why we should recycle. It dramatically decreases the energy it takes to produce goods, and it allows our matter to stay with our society, so prolonging the life of our society. We wouldn't run out of high quality resources. Like all the chemicals that are inside your computer as you're looking now, those high, very expensive chemicals used to make high quality computer chips. So now we're into energy. Energy is the ability to perform work, to do work, or heat. So we've got the ability to do work or heat. So work is whenever an object or something is moved. And we do have two types of energy. Kinetic energy. Kinetic means to move. So kinetic energy is moving energy. So a car moving, that's kinetic. Water flowing through a pipe or down a river is kinetic. Light moving from your computer screen to your eye, that's kinetic energy. So kinetic energy is any energy that's moving. Electricity moves down a wire, it's kinetic. Potential energy, that's energy that is stored. It has the potential to do work, but it's not doing work right now. It's just potential energy. So electricity stored chemically in a battery is potential energy. Wood that could be burnt to generate light and heat, that potentially could do work. Wood is potential energy. Gasoline's not doing anything right now. That's potential energy. And you've got a bunch of potential energy in you, stored potential energy in your muscles, so at any point you could get up and go make yourself a cup of coffee. Now, energy is governed by two laws, and these are the first laws that we talk about in this class. They are the first and second law of thermodynamics. The first law of thermodynamics says that energy cannot be created or destroyed, but it can be changed from one form to another. So you cannot make energy. You cannot destroy energy, where there's always the same amount of energy. But you can change it from one type of kinetic energy to another type of kinetic energy, from electricity to light, or from potential energy to kinetic energy. So you can go from electricity to a battery. Your battery charger on your car will store that energy, so it goes kinetic to potential. And then the battery can give it back out as electric, so it goes from potential to kinetic. So the first law, you can't create or destroy energy, but you can change it. Second law says that when converting energy from one form to another, useful energy is lost. So that's useful energy is lost. Not the energy is lost, just its useful energy. And we're going to look at these in a little bit more detail. So we're going to do the first law again, and then the second law. We'll add a little bit more detail to this. Alright, so first law of thermodynamics. Energy cannot be created nor destroyed. Let's look at that part. If you want to move your car, you can't just generate energy to make your car go forward. You have to get the energy from somewhere. And you've got two choices. One is you can get the energy from your muscles. You stand behind the car and push it. Not the best choice. The second one would be to use chemical energy from gasoline. You put the energy of the gasoline into the engine converts it to kinetic energy, the kinetic energy moves the wheels, moving the car along. So you didn't make that energy. The energy to move the car came from the gasoline. Now we need to think about where the gasoline got its energy from, because it's obviously it can't just be generated spontaneously, it had to come from somewhere. And gasoline gets its energy because it's made from oil. Oil is the decayed remains of ancient marine life, so it's ancient plants and animals that lived in the ocean. Those animals got their energy from the plants that they ate. The plants got their energy from photosynthesis, from doing photosynthesis of sunlight. So the plants got their energy from the sun. So let's trace that again. It goes, movement of the wheels comes kinetically from the engine. Engine gets it from the gasoline. Gasoline from the oil. Oil from ancient marine plants and animals. Ancient marine animals got it from the ancient marine plants. The plants got it through photosynthesis using sunlight. So really the energy moving your car is packaged sunlight. So one of the things that we say is that the ultimate source of energy for living things tends to be sunlight. The ultimate source for 99% of living things on our planet is going to be packaged sunlight. Even if we were doing you push the car, that was still packaged sunlight. If you're outside pushing the car, the energy to turn the wheels is coming from you physically pushing with your muscles. Well, where'd your muscles get their energy? They got their energy from your food. Alright, so say you just had breakfast and you're on the way to work and your car broke down, that's why you're pushing it. And you had sausages for breakfast. So the energy is coming from those sausages. Where'd the sausages get the energy? They get it from the pig. Where'd the pig get the energy from? He got it from what he was eating, the corn. Where did the corn get the energy from? It did photosynthesis from the sunlight. So we packaged sunlight into corn, that then packaged into pig, then packaged into sausage, then packaged into you, then packaged into movement of the car. So again, we didn't generate any energy. The energy is coming from the sunlight. First law of thermodynamics. And we're not losing energy, we're just changing where it is. We're moving it from the pig to the sausage to you to the movement of the car. Now people ask where the sun gets its energy from, and the sun is a nuclear fission reaction. And when we do nuclear power, and you read that section in the book, you'll see how nuclear fission functions, and you'll be able to get that info when we do that later. Right now we've got to zip on and do the second law of thermodynamics. Alright, so our second law says that every time you do energy change, useful energy is lost. And that loss usually comes in the form of heat. So useful energy can be used to do things. Gasoline can move your car. Wood can cook your dinner or light your way. Muscle power can move your body. But heat is considered useless. Once we have heat in the room, you can't do anything with it. So we're going to see that energy will move from kinetic energy towards heat, which is a type of kinetic energy. And this energy is just so dissipated, so spread out, that we can't use it for anything anymore. And we'll use your car example to start with. So we've got our car example. We've got the gasoline in the car's moving forward, but only about 10% of the energy will push the car forward. 90% of the energy is not moving the car. A whole bunch of the energy makes the engine hot, makes the wheels hot, makes the brakes hot, puts heat onto the road. So if you drive your car and you've put $10 worth of gas in the car, you're only getting about $1 worth of movement. The rest of it, because of the second law of thermodynamics, just goes to heat up. Heat up the engine, heat up the coolant, heat up the transmission, heat up the tires. So the next time you drive your car, don't touch the engine, too hot. But touch the tire. You'll feel the heat on the tire. Touch the bonnet, the hood of the car. You'll feel how warm that is. So our second law of thermodynamics is losing energy, and it's normally lost as heat. And we know that light bulbs do the same thing. About 10% of the electricity going into a normal light bulb makes light. About 90% of it's making heat. So if you leave a light bulb on and then touch it, and I'm sure you've done this at some point in your life, it's really hot, you burn your fingers. And your muscles are no different. If we get you up and make you do jumping jacks, the energy is supposed to be moving your body in those jumping jacks, and what it does is move you and makes you hot. You generate a bunch of heat. As you get hot, that's second law of thermodynamics working. You're losing useful energy as heat. So energy also has quality. And we see that there's high energy quality and low energy quality. So if there's lots and lots of energy in a very small amount of space, that's high quality. So electricity, lots of energy in a small amount of space, high quality. Gasoline, lots of energy in a small amount of space, high quality energy. And the worst quality energy, the lowest quality energy, that would be heat, spread out in the environment. Now, what you can see is that as we use energy, we change high quality energy into low quality energy. So we take oil, turn it into gasoline, so we've got high quality energy, and then burn it in your car and get out mostly just heat in the air, low quality energy. And once it's done there, we find it very difficult to utilize that low temperature heat, that low quality energy for anything else. So we can't stop that happening. The second laws of thermodynamics say that every time you use high quality energy, it's going to become low quality energy. But what we can try and do is slow down the conversion as much as possible. Use as much as the energy for the jobs that we need it to do, and slow down how much heat we're generating. So one of the activities you do in the class is you look at different light bulbs and you compare normal light bulbs with compact fluorescents. Compact fluorescent bulbs make much less heat. they use much less energy, not because they produce less light, but because they don't produce as much low quality energy per unit of light produced. They're just more efficient. So efficiency is how much work you get done per production of low quality energy. The more work you do for the lower production of low quality energy, the more efficient an item is. So more efficient cars get more motion out the car with using up less gasoline. They produce less heat. Now we said that it's not just things within our lives that are governed by the first and second law of thermodynamics. All living things are governed by those same laws. So when grass generates its food through photosynthesis, the first and second law of thermodynamics occur. When deer eat that grass, the first and second laws of thermodynamics govern the flow of energy. So when we look at how energy passes through biological systems, passes through a forest, passes through a farmland, it's really no different than the energy passing through a car. It's, in our car example, we went back to the ocean and we said our oil comes from old sea animals that were eating minute seed plants. That's a biological system. And lastly, on energy, this link between pollution and energy flow, this pollution and thermodynamics. So one of the consequences of energy conversion is going to be pollution. And we already did what pollution is, so make sure you know that definition of pollution. Make sure you understand the definition of fitness. Make sure you've got those. So as we do modern day work, as we convert energy into products, we use energy to generate products in a factory, we're going to generate some pollution. Some of it will be thermal pollution, heat pollution. Some of it will be particular pollution, particles that we put into the environment. Now, if we want everybody on the planet to have a useful amount of energy to use, remember we said that in less developed countries that's about 80% of the world's population, and yet they only use about 20% of the resources. Well, how do we do that? How do you get all that extra energy to those people? There's not more and more energy keep being delivered to the planet. So one way to approach it is just to be more efficient with the energy that we have. We said that the car at the moment uses about 10% of its energy to move forward. Well, let's try and change that. If we can use less energy to move forward so that we can use less gasoline to move the car, or maybe not gasoline at all, a different subject that's more efficient, then that extra energy can be used by somebody else. So we can be more equitable with the energy supplies that we have so that other people can utilize that energy. So not just more developed countries can drive cars, but so can less developed countries. Now you need to understand that less developed countries are going to drive cars anyway. This isn't a choice where we go, no, we'll keep the cars and they won't have them. If you look at the growth rate in China and the growth rate of India, just how fast car development is growing in those countries, those people will be driving cars. If we don't approach this from an efficiency viewpoint, all it does is it means that they use up gasoline at a faster rate, the price of gasoline goes up, and you have to pay large amounts for moving your car. If we tackle this and try and get more efficient vehicles and get ways that won't use up gasoline as fast, then the fact that all those Chinese people, those Indian people, the Pakistani people, the Bangladeshi people are also driving won't impact you in decreased amounts of oil and won't hammer your pocketbook quite as hard. And not just your pocketbook, we're really talking about your great-grandchildren. Okay, and the last slide for this. As we are looking around and looking at our matter that's available, and we started this set with matter and saying how there is high-quality matter and low-quality matter. notice that our resources, which are our matter and our energy, also comes in two different types: renewables and non-renewables. Renewable resources are resources that do not degrade, as in we don't run out of them. So solar power doesn't disappear. It doesn't matter how many people are using solar energy, the amount of sunlight is not less because somebody has a solar collector. Winds and the tides flowing and rain is a renewable resource. As long as we use them carefully, they will always be there. Now, obviously, if you use up all the water, you can deplete a river of flowing water if you suck it out and spray it all on the fields. But as long as you use it carefully, water will continue to flow, and we will always have those resources. Non-renewables, well, those are in a finite, a limited amount, and no matter how careful we are, we'll run out of them. So our fossil fuels, our oil, our coal, our natural gas, at some point will run out. When that happens is up definitely for debate, but what isn't debatable is at some point the oil reserves on the planet will be gone and we will have to use something else. So the iron on the planet, there's only a finite amount of iron, and if we don't use recycling, then we will run out of iron to use. Iron happens to be one of the most recycling industries in the world. They do a fantastic job of recycling that metal. But there are others that we have not caught up with the quality of our iron recycling. And then we have the potentially renewable group. Potentially renewable, classic example would be chickens. Chickens should be completely renewable. We should never ever run out of chickens, because as long as you leave a couple of chickens to mate, they make new chickens for you. However, you have to be careful. Obviously, if you killed every last chicken, there would be no more chickens. They would no longer be renewable. So this group require that you actually are a little bit sensible in your management. Right? You can destroy the soil. You can pollute the fresh water and use it all up. As long as you're careful in your usage, then they will be around for future generations.